Okay, so I'm going to just honestly briefly touch base on just a few words for atomic structure, just because it was covered at that one Saturday, and then one day after school we also went over it. So I don't want to spend too much time on this because it cheats the people who've been doing the review sessions. So, so the first thing we're going to talk about is just these dudes. These are just a few that I picked from the list because I feel like you should remember them. What did Thomson discover? The electron. Okay. Planck or Planck.
Planck constant.
Okay, but what was more useful to us?
Energy and something.
Yes, kind of. So it's quanta. He came up with a quanta. All right, quantization of energy. So what that means is a packet of energy. He defined what that packet was. That's why we have his little constant there. Okay. Rutherford. What did he discover, you guys? Nucleus. But yes, so you could say proton. You're fine. All right. Bohr.
The Bohr model.
So the Bohr model, but what is the Bohr model showing us? Why do we use the Bohr model?
Valence electrons.
It's not valence electron. The rings, which are energy levels. There you go. That's the part that's useful to us. Okay. We shouldn't really be relying on the valence electrons as much with that. Okay. All right. Heisenberg. Uncertainty. Yes. All right. And so just a quick overview of that one. It's the idea that you can either know how fast something's going or where it's located, but you can't know both. So it has to do with where electrons are going to be located. So it's kind of the cloud idea. But Schrodinger came up with that, and then Heisenberg had the uncertainty principle. Yes. Who is? There's a chance. Sometimes they refer to them. Take one of those packets. Explicitly, like what did they do? No. But it's good to know a little bit of background about it. Does that make sense? Okay. All right, and then Chadwick. Does anybody remember him? I'm going to spell this wrong. Neutron? EU? EU. Yeah, all right, we're good. Okay. All right. So all good with that? Yes? All right, cool. I heard a lot of ahs. All right. I'll write underneath it. So, kind of a review from your little pre-AP year, your little 8-man. How do we determine the identity of an atom?
Number of protons.
Great. Number of protons. Okay? So every single time your number, oh, that's not a good color to use. I won't use that color. So every time that you are trying to decide who you're talking about, their number of protons is always going to stay the same, right? So it's their atomic number up there, all right? So that's your atomic number. Make sure you don't forget that. That's your guarantee. Everything else is you have number of electrons. If that changes, what do we have? Yeah, if we have a change in a charge, what did we just create?
An ion.
An ion, good. And if we change the number of neutrons, what did we?
An isotope.
Good. We have an isotope, which is like different weights of the same thing, kind of thing, okay? Different masses.
All of them are stable.
And not all of them are stable, good. So in our review session earlier, we kind of talked about that little distribution graph. And so just make sure you can read that the highest part, that's the most common isotope on those graphs, okay? All right, I'm going to flip it. The heaviest two out of those three. Right, protons and neutrons are what make up the mass. Electrons tend to be pretty negligible when you're thinking of simplified model, okay? Huh?
Is that particle that actually gives the atom's mass?
What? Neutron?
What's the name of that particle that actually gives the particle?
Oh, or did I not need to do that? Okay. What is your heaviest two particles, by the way?
Its mass.
I don't know, Google it. Okay. You on your AP chart have this one. Okay. So just quick review. Who is that? Oh man, speed of light. Good. Okay, and I believe they provide it to you. They give you the number. Yeah. But just in case you guys ever forget it, it is so there. All right, so 3E8. Okay, what is lambda used for? Wavelength. Good. And what is this V used for? Frequency, exactly. That's the awkward thing from physics to chemistry, right? So it is not velocity. Don't make that mistake. Okay. And then we had the E was equal to HV. So this one right here is what? Energy. So when we're looking at this, we're looking at an energy of a photon, I believe, a little particle. Okay? And then H is Planck's constant, Planck. And this one is still, sorry, Miana. Okay, and then that one was frequency as well. All right. Okay, so we got all those. Another one that was important for atomic structure was not an E. It was the Q1, Q2 over R squared. Okay? It kind of looks like somebody's law. Usually there's a little K there. Whose law is that? What is that?
Coulomb's law.
There you go. All right, so Coulomb's law. We don't really focus on that constant so much when we're talking about it, but the reason I want to review that is because, and especially people who went to the review session that Super Saturday, that is your answer for a lot of things. Your ionic bonds, why things are attracted to each other, why there are trends on the periodic table, and it has to do with, you can either say electrostatic, so write these two words next to it. Electrostatic attraction, or electrostatic forces, whatever you want to say, or Coulombic attraction. You can use either of those words, and that is talking about positive and negative being attracted. Okay? So anytime you come to a question where that's what you're describing, that's what you're thinking. So electrostatic forces or Coulombic attractions. Okay? Okay. All right. Then we had quantum numbers. You are actually not going to be tested on those. So, but I don't mind us, at least you should know that they exist. So we are just going to put them on here, but you do not need to memorize like those letters, and you don't need to memorize the order of them. The only one that you're ever going to be tested over is N. But this going over these is what's going to review what makes up the address of everything on that periodic table, right? So this has to do with orbitals. Okay, so I want you to think orbitals again. There it goes. All right. So with orbitals, what is the first one talking about? That's the one that you're going to get tested over. So you got to know that one at least. What's the N for? When you want to know the location of an electron, what's important to know? Something about the cloud, yeah. This one's your principal quantum number. So this one is your distance. So this is like your energy level. So on the periodic table, sorry, that's energy. That is a Y, not an E. All right, energy level. So on the periodic table, how do we get our energy levels?
Rows.
The rows, right? But they're actually called Periods. Yes. All right. Okay. The L is going to be your orbital quantum number. So what do you think that one was? If we're talking about an orbital, what are the different orbitals that we know of?
SPQ.
There you go. No. SPDF. Okay, so we have our SPDF. And if you remember, when we talked about SPDF, S is the one that looks like that. P is like that. Ooh, that's not right.
It looks like a peanut.
Oh, yeah. Okay. And then D is like 2 of those. And then F is like weird that we don't really worry about. Okay? All right. Okay. Your magnetic quantum number. So what that means is, remember when we had to do our up-down arrows? You're either the first one or you're the second one. Okay? It's talking about, and then when you had your different spaces, which spaces were you taking up? Okay?
Which ones were the exceptions to that little rule? Which are the ones?
So the ones where you're filling up the in the d orbital, or you're transitioning to the p. So I want to say starting at gallium on your periodic table. That one definitely, because you're going from D to P. So it just depends where you're at. And then also we had the ones that are halfway through the d orbitals. So wherever that is, if you look on your periodic table.
Was it chromium?
Yes. No,
Wait, that was
I can't count.
19.
Yeah. It's up there. It's over there. All right. Anyway, spin number just means are you going forward or backwards? Okay. So it's usually a positive or negative. But like I said, they're not going to test you over like knowing what those letters are. Just know that these are what make up your whole thing, because these are the different guys that came up with the different principles. All right. So I really quickly wanted to see though how to write your little orbital notation stuff. So you know that we've got, what is this block over here?
S block.
That's your S, okay? So you would say 1S2, 2S2, right? Those are the first 2 rows. Then where would we go after that?
P1.
No. P1. Is that what you said?
2P.
Yeah. So we would say 2P6. Right, and then 3S2. And then we would go 3P6. And then we would go 4S2. Oop. Yes, now we're entering D, but we go back 1, right? Energy level. So this is 3D10. And then 4P6. And then so on and so forth. And when you get to the F block, just know that you go back 2. Okay? So wherever F block is going to fill in. Do I need to clarify anything here with you guys? So remember, when you're looking for something on your periodic table, you can just focus in on what the last one is. Double check that they're all filled, right? So double check that you got 2s and 6s and 10s and things like that. As long as you don't have an excited atom, you can always kind of look at that last one and you can say, all right, I'm in the 4th row, I'm in the P, all the way at the end, 6. So I'm that guy, okay? So just know that you can always map it out that way quickly and find whatever they're asking you about, okay? Okay, I don't want to take the whole class period on this. So I'm going to go into the next one. Okay. When you also have your periodic table, these are lovely periodic tables. There you go. All right. So when you have your periodic table and you're trying to come up with your different trends here, okay? Remember that our argument going across is called what? I gave you guys this, but you got to know what that is. Make sure you write this down, please. Effective nuclear. Ooh, not an M. Nuclear. Just kidding. Nuclear charge. Okay, so what does that mean? How effective is your nucleus pulling in, right? So more protons is what you're thinking. More protons, more pull. Right? You guys kind of remember that now? So if they're asking, why is this one smaller than that one? Or why is that one bigger than this one? Or why does this one have a higher ionization energy? Why does this one have a, you know, whatever they're asking for. And we'll go through those words one more time real fast. But remember, across the periodic table, if you're comparing things that are across from each other, not at different energy levels, they're at the same energy level, so same layer. It has to do with how many protons are pulling in on electrons. So how easily are they communicating to the stuff on the outside? Okay? All right, when you are traveling down your periodic table or down a family, what's that one? Shielding effect. Good. Good. Shielding effect, okay? And so shielding effect is like layers. Okay? So if you increase layers, you decrease, I'm going to put communication. Okay? You decrease communication, meaning it's not going to be pulling as effectively on the outer stuff. Okay? So you decrease that communication. If you want to say decrease pull, I guess you could say that too. Okay, so now let's really quickly review what the trend was. So atomic radius. Which corner is the big corner? Which one's the small corner? Big, small, right? Okay. And do I have to review what radius is? I hope not. Okay, that's good. All right, ionization energy. So this is ionization energy. So this is going to be energy needed to remove an electron. So who is that kind of very similar to? What other? Electronegativity. I would say electron affinity. Do you guys remember affinity? Electron affinity? We're going to put that one with it too. What? Oh, my phone's getting there. Hold on. Better? Okay. All right, so electron affinity is just how easily it's going to gain an electron to form a negative ion. All right, so I told you guys, remember that one with a heart, okay? But both of those are kind of the same. So which corner has high energy needed to remove an electron and high want of electrons? Top right, exactly. So we're going to put a big heart over here, and that's to represent both of these, okay? And this one, we're going to put a tiny heart. So due to less effective nuclear charge and more shielding, not as much energy is needed to remove an electron, and they're not as likely to give up stuff to do that. You guys okay?
Yeah.
Oh, okay. All right. We also have, so electronegativity is also going to follow the same thing, but I'm going to put its definition on a new slide if that's cool with everybody. Actually, you know what we can do? Shrink it. Can you guys still see it? We're good? Okay. So, electronegativity is your ability to bond. Okay? It's your ability to attract electrons. It's your ability to bond. So electronegativity only matters when we are looking to bond it with somebody. all right? That's usually when we only bring it up. That's why electron affinity, ionization energy tend to be things that we can just talk about something individually. Electronegativity doesn't come into play until we're trying to mix it up with somebody, okay? All right. I am good. Oh, dang it. One more thing. Okay. What is this? Absorbance versus molarity. What is this graph representing? Somebody's law. Adults like to drink it. Beer. Beer's law. All right. I'm just kidding. All right. So Beer's law. So all that you need to know about Beer's law, which is on your periodic table, it's A, B, C. You won't be really plugging into it. What you need to know is that absorbance and concentration are directly related. And that's what this graph is showing, is that if we can measure absorbance, we can then assume molarities or concentrations. So you guys, if you remember, you guys used it when we did the bullet casing one and when we did the kinetics lab with Crystal Violet. Those were the two main ones where you were able to figure out concentrations just from looking at absorbances, okay? So, cool? Cool? We're good at that? All right. All right. The next one I'm going to talk about, sorry. Okay, I know what we're going to talk about. All right, and today, after school, we are going to go a little bit more in detail on what I'm going to go over right now. So we're going to practice after school for sure how to figure out your different shapes, and we're going to practice memorizing them a little bit, okay? But, so your different bonds, so this next section is going to be about bonding, okay? All right, so we know that we've got ionic, which, what is the force that attracts those? We just went over it first slide in the last one. Electrostatic. Electrostatic forces, okay? Meaning positive, negative. That's Coulomb's law, Coulombic attraction, okay? Okay, metallic bonding. What's the big idea about metallic bonding? Does anybody hold on to their electrons? No. Okay, so it's a metal with a metal. And they have a sea of electrons. I heard somebody say it. Okay, so those electrons just kind of bounce around. Okay, and this one, sorry, I should have said metal, non-metal. Okay, and then the last one we had was covalent stuff, which tends to be a non and non. Okay, covalent happens when you have similar electronegativities, right? So remember I said that word only comes into play when we talk about bonding. Ionic has different, very different electronegativities, okay? And that's really, truly, this is how you decide what kind you have, okay? It's based on their electronegativity numbers. But I've told you guys that you can also figure that out just looking at your periodic table, because they don't always give you those kind of numbers, right? So looking at the periodic table, if we know we're dealing with two nonmetals over here, okay, how can we figure out if they are going to be polar or nonpolar? And remember, polar is more like ionic. right? It's not completely ionic. It's not electrostatic forces. They're still sharing electrons. I guess I should have said that. Sorry. But how can we decide if something's polar versus nonpolar?
Electronegativity.
Electronegativity, but we're not given that value. We're just given a periodic table, and I say something like fluorine with 10. Distance, exactly. So if I have something way down here and something way up here, that's going to be a pretty big electronegativity difference. Okay? If I have things that are right next to each other, is that very much of an electronegativity difference? No, okay? So so don't forget that location helps you decide whether something's polar or nonpolar.
But they're far away.
Huh?
If they're far away.
If they're far away. No, oh, if they're far, they're polar. And if they're close to each other, they're going to be nonpolar. And remember, all your diatomics obviously are also nonpolar. Okay? Okay? All right. Those are just a few words so that when you see them, you don't freak out on your multiple choice. Okay? So bond length. What is the bond length between? Is it cloud to cloud? Is it nucleus to nucleus? Is it nucleus to cloud? What is it? It is not cloud to cloud. It is nucleus to nucleus, yeah. Okay, so especially my physics people, remember when you guys did gravitational force? It's the very center of mass, the center of mass. That's the idea, okay? So bond length. So obviously bond length is going to be affected by that Zeph and your shielding effects, right? So big atom with another big atom is going to have a huge bond length, all right? So their forces of attraction are not as much as something with smaller bond lengths, okay? So these things do affect attraction, okay? So their atomic sizes are going to affect attraction as well, how strong their bond is, all right? All right, bond energy. What is bond energy?
Amount of energy between bonds.
No.
Amount you need to break it.
Yeah. Energy needed to break. So this is like when we were doing thermo and you had that big list of all your different bond energies. That's what that is. So you gotta, when you're looking at different bond energies, when you're looking at different bond energies and you're trying to figure out which ones to do, you gotta look at how many of the types of bonds there are. Okay, so you have to actually draw out the structure and figure out, oh, there's 4 between C and H, and then multiply it by 4. Okay? All right. Bond order. Okay, bond order. Does anybody remember doing this calculation? Yeah, I figured. All right, here you go. Bond order is equal to half the number of your electrons that are bonding minus your electrons that are shared. Oops, that means the same thing. We should say antibond. There we go. Sorry. So the ones that are not, okay? This would most likely show up on a free response? That's just a side question. You would probably get away with not knowing how to do it if you don't want to go back and look at it in your notes, okay? But, all right. Let's also look at, we learned about this and this. What was this one?
Sigma.
It is a sigma, but it's a sigma bond. So what do we use that for?
Metallic. One-on-one bonds.
Yes. Did you say one and one?
Yeah.
Yeah, single bonds. Okay. Okay, and so what that one's talking about for sigma was the two things, and they have that bond like that. Okay. When you're talking about a pi bond won't exist by itself. Okay, it has to be in court, like along with your sigma bond, and that one was the idea that you're bonding two areas, so it's a lot stronger. So that should tell you. Okay, this will be single. Let me write it off to the side. This would be double. So what is triple going to look like?
Sigma pi pi.
Sigma pi pi. Good. Okay? And I would say you're good with just that. Just being able to recognize that. Okay? I would take a second and just review resonance structures and dipole moments. Not dipole moments, sorry, just resonance structures. So remember with your resonance structures, it's the idea of your lone pairs kind of swinging around and the bonds moving around. I do not have one off the top of my head that I can remember right this second. Was it carbon? One with, I'll look it up and I'll get one to you guys again. But there was just one where you have your different probability of it being in that structure. And so there's like a more stable version of it, but the whole time it's going to be swinging around. So just know that resonance structures are out there. Okay. All right. Dipole moment. So that leads us kind of, if we're going to talk about dipole moment, that'll be IMFs. So after school, like I said, I will go through the different shapes again. And I'll try and record whatever we do. So that way if you have to miss today, you can do it at home. Otherwise, it's on page, a good easy table is page 24 in the chapter 2 little section. Okay, so if you want to just kind of look at that real quick, you can. All right, so when I'm going to talk about dipole moment, we're talking about intermolecular forces again. Okay, this is a new section. IMFs. Yay. All right, so what is the most common IMF? No. So remember, yes. So they are split between our nonpolar covalent. They're only for covalent, right? And they are inter, meaning not bonds, right? So what they mean is they're like little strings that are holding together the molecules, all right? This is what gives covalent things that low melting point, is you're able to break your intermolecular forces super, super easy, okay? But you have different forces between your two different types of covalent bonds, okay? So your nonpolar, you guys said, was London dispersion. But we also know that's also true for polar, okay? It's actually found in everything. But it's not prominent in polar. That's the big idea there, okay? For London, or actually let's just go over to the polar one real quick, and then I'll come back to London dispersion. So for polar molecules, what do we call their intermolecular force? Dipole. Okay? So what that means is you have positive and negative things just being attracted on two different molecules. Okay? So this is attracted to, or whatever. Yeah. Yeah, so there you go. So these guys are just being attracted to each other, so they're, whatever, coming together. Okay? So it's an intermolecular force. It's easily broken. But this is a stronger one than your London dispersion. Okay? All right. Then you had... Yes. I have to give myself room. There we go. Then we have H bonding. And what was our saying? H bonding is? F-O-N. Good. So what that means, it is limited to when H is attached to an F, an O, or an N. Okay? So the H actually has to be attached to that. So it can't be something that has an O off of the N and then that you think it's magical. Woo! No. It actually has to have the H attached to those. And then you're going to have those H bonds between the different molecules. So water obviously has the H2O. Both of those are attracted to the oxygen. So that consists of hydrogen bonding in between them. Okay? Which is why we can boil water and freeze it and all that stuff. Okay? All right. London dispersion. So let's come back to that for a second. Okay? London dispersion forces rely on dipole moments. Okay, and these dipole moments are, who remembers, it was like a very animated day that day when I was lecturing. So if I have like diatomic molecules, so let's just say we have like O2, okay? So we have O2 with a bunch of other O2s or whatever, okay? Versus somebody like Br2. What was the difference between our O2s and the Br2? Huh? Their size, right? So size has gotten bigger on both of these. Or I'm sorry, size got bigger with bromine. So who's going to have more of a dipole moment? Who? Bromine, yes. This guy has bigger dipole moment. Right. So if you guys remember, it's squishability. Do you guys remember that? Your polarizability. That's actually the word. Polarizability. So what you're imagining is this has this big cloud. As they're colliding with each other, it kind of moves the electrons over to one side at one point. So now I have a negative positive end. Now I have a dipole moment, and they're going to be attracted to each other. Okay? So your larger atoms are going to have the bigger dipole moment. So those dispersion forces will be stronger versus our smaller guys like O2. Okay, so go ahead and make sure you label these so that you know what you're looking for on your periodic table. Okay, so O2 has a smaller dipole moment than Br2. And that's why Br2 is a liquid, sorry, not solid, liquid at room temperature. Okay? And it has to do with having more ability to polarize. Bigger cloud, bigger squishability. Okay? Big fluff ball. That's what you want to think of. Okay. Let me do one last thing with covalent stuff. So remember that you had this is classification. You had a table like this, and if you know where that is, then I wouldn't bother writing this down, and I would just go study your table. If you think you've lost it, then write this down really quickly, okay? So we had 4 different types of structures that we were supposed to remember. One was an atomic, was an atomic or molecular crystal. One was metallic. I was using the wrong side of my staff. One was ionic. That's better. And the other one was covalent. Okay. So for all of these, we have the bonding strength. You should already know what is keeping them together. We already went through that. So bonding strength, this is going to be very weak. So this is like having pure whatever on the periodic table, okay? But not including the metallic ones, okay? So anything on the other side. So strength is weak on that one. This one is moderate to strong. This one is strong. This one is very strong. Okay, so it is really hard to break apart covalently bonded things, but the IMFs are super easy to break, which is why they'll melt. Okay, there's no easy way to do this. I will actually post this picture. Here. I'll even put it right now. And then you guys can just look at it as you need. So there's this little picture. So if you need it, you can print it off of the thing. Okay? And that way you don't have to sit there. I thought it was going to be a little bit easier. So this is on page, if you want to know, is 52 in the chapter 4 one. But that's kind of all we've got time for. The one that I did not go over was gas laws. If we can today after school, I will try to. Otherwise, read through it. It's not bad. Actually, we have 1 more minute.